Okay, so question 1 is basically just an ideal ranking cycle. Okay, so let's see. So the boiler operates at 2000 kilopascal, while condenser temperature is 50 degrees Celsius. So rather than giving you two pressure this time, this question gives you one pressure, one temperature. So the saturated liquid enters the pump. So at state 1 is saturated liquid, and the turbine exit produces a steam mixture with a quality of 94.97%. So in this case, it's diagram. Usually this gas include the work as well. You can don't put the temperature and all, but the work and the heat you should include that. Okay, so let's say we do a TS diagram. Okay. So this is a 2000 kilopascal. So at the bottom, this is not. We technically don't know what the pressure, but of course we can find it out from the table as well. But we know that at this point, this is 50 degrees Celsius. Okay, so and you can just sketch it this way. So this 1, 2, so 1 is saturated liquid. So 3, 4. This ideal cycle, so we should just show something like this. Now, always bear in mind, 1 to 2 and 3 to 4 are isentropic process for ideal. For actual, you sometimes also draw that line. So make sure that this is a vertical line. Don't slant to one side. Okay? So 1 to 2 and 3 to 4 are isentropic process. They should always be vertical straight line. Oh, okay. So at least you need that 3 throughout. Just include it. Okay, so always start with assumptions. So we'll say the operating conditions. So negligible change in K and E. Okay, so we can start from state 1. Again, this is an ideal cycle, so everything is pretty straightforward. So at state 1, we know that T1, so unlike usually the question, usually I give it T1. So in this case, I give it T1. So we use T1, and you know that this is saturated liquid. So based on this, you can find H1. You can also find D1. So these are the things that you need. And of course, you need to find P1 as well. Because otherwise you can't move on to state 2. So now we move on. So 1 to 2 is isentropic compression. So we have learned that for pump, so this pump, right? For isentropic compression, you can find the work being based on P1, P2 minus P1. This is why we need to find P1. And also we know that H2, this is H2 minus H1. So from here, you can get H2. So usually, we will move on to state 3 in this case. But here, we don't really know anything about state 3, right? Because state 3, all we know is that is T3 is 2000 kg. At this point, we know nothing else. But of course, we also know that since it is ideal case, S3 is equal to S4. But we don't have S4, so we need to move on first, because for now we don't have this value. So we move to state 4. So state 4, we can find something. Because at state 4, we know that T4 is 50 degrees Celsius. You can use T4 equals to T1, but then that you will need to interpolate, so it covers it. So you can directly use T4. T1, meaning T1 and T4 is the same. So unless state 4 is in superheated state. If T4 is in superheated state, then you cannot use T1 now, because then it won't be the same value. But if it is still in saturated state, these two should be the same value. So we can directly use this. Don't need to use T1 equals to 12.352, because that one you need to interpolate a bit shorter. So we keep this, and we know that x equals to 94.97%. Or maybe I prefer 9497. So then you can find H4, you can also find S4. So once you found S4, then you can get H3. Of course, question also asks for determine the turbine inlet temperature, meaning you need to find T3 as well. So T3 is approximately 600 degrees Celsius if you calculate it. So of course, if you manage to reach this state, then the rest shouldn't be any issue. So thermal efficiency is just, so you can use work net over Q in, or you can use 1 minus Q out over Q in. These two are fine. You just need to find the work net and the Q. So if you use work net, you need to find work out, because the work-in is in the first question, right? I mean, say 1, say 2. And the power output should always be the net power output. So this will be m dot work out minus work in, okay, or q in minus q out. Okay, these two are the same. So the value here for thermal efficiency, it should be approximately this value for the device one. Work net should be about 2.4 megawatt. So again, this entire question, problem 1, by right you should be able to solve this. Okay, so because this is the basic fraction. So if you have problem understanding this question, then you need to let me know. Okay, because out of these 3, this is the most basic one. Technically, 2 also is basic in terms of the calculation. The theory part is not the details there. Okay, anyone has any question for this? Three, two, one. If not, we'll move on to question 2.